one of the most widely recognized physicists, Michio Kaku, has discussed his evaluation concerning this issue. Kaku, known for his significant contributions to the fields of physical science, has recently acknowledged that the James Webb Space Telescope, JWST, has found 6 enormous galaxies that experts once thought could not exist. These discoveries have the potential to open up new perspectives on how we might interpret the universe. It is therefore both fascinating and worth monitoring these developments. Kaku is a remarkable figure in the scientific field. A physicist of American and Japanese heritage, he is regarded as an expert in both traditional exploratory physics and quantum mechanics. Unlike some more conservative and skeptical researchers, Kaku has been open to the astonishing recent discoveries of the JWST mission. We are fortunate that this distinguished scientist has chosen to end his silence and openly share what can no longer be denied. The enthusiasm and almost all-encompassing tone of the famous physicist are apparent in his comments on the discoveries made by the James Webb Space Telescope. He proposes that these findings have been the catalyst for his renewed interest. Let us explore the implications of Kaku's revelation of these 6 massive galaxies. Kaku is a scientist who has always been willing to consider new theories throughout his life. He understands that Einstein's theories of relativity and Newton's laws are insufficient to capture the full complexity of the universe. Kaku recognizes that the revelations from the new telescope might potentially improve the scientific field, even though many of his peers have not embraced this view. This has caused concern and anxiety among both defenders and critics of quantum mechanics. However, this genuine understanding brings out laughter from Kaku. The JWST has uncovered the discovery of 6 enormous galaxies tracing back to the earliest phases of the universe. Each of these vast systems contains more stars than our own, despite forming just a short time after the Big Bang. The group of astronomers who made the discovery has named these surprising galaxies universe breakers, as their existence could change our entire understanding of the universe. Something here no longer fits with the theory of the Big Bang. The Big Bang theory suggests that the universe was a chaotic place following the initial event. The first solid objects took several hundred million years to form, and it took billions more years for these objects to reach an adequate density to produce light. The development of complex structures, such as galaxies, was expected to happen much later. Some of the newly discovered galaxies outperformed the size of the Milky Way, and their enormous brilliance suggests they were likely forming many new stars each year, while our own galaxy forms stars only irregularly. It remains unclear exactly when the first galaxies formed. Researchers have not been able to determine this until recently. The one thing that is clear is that, at first, there may have been only single stars or groups of stars that eventually came together to form continuously larger structures, eventually leading to the development of dwarf galaxies, which underwent mergers and continued to grow as past hypotheses have suggested. According to these hypotheses, very advanced and massive galaxies could not have existed at that time, which raises the question of whether the universe is simply older than previously thought or whether complex large-scale structures existed much sooner than expected. This current situation presents a challenge for conservative science, which still struggles with this model. Also, some areas of physics have firmly dismissed this revelation, highlighting potential errors in the age calculations. Kaku, mindful of this, had this to say: "There are many instances of old and misleading theories that stubbornly endure due to the prominence of certain scientists. Many of these hypotheses were eventually disproven when fundamental investigation uncovered their misrepresentations. Hence, the vital work in any science, especially in physics, rests with the experimentalists who maintain the validity of research through exact truth. As a matter of fact, on Earth, we have essentially no information on the genuine origins of the universe." The Big Bang theory was established in 1927 based on observations of the universe's expansion. This information led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to imagine a universe with both a beginning and an end. The possibility of a universe that had always existed and was infinite in time was beyond human imagination. Indeed, even today, scientists still face challenges in understanding it. Nevertheless, it is essential to reconsider these possible outcomes. These new insights do not align with what scientists have relied on for years with the Big Bang theory, but science has repeatedly shown that reassessment and openness to groundbreaking ideas are key pieces of the scientific process, as much as the affirmation of specific theories and observations. When Einstein was a child, it was believed that the stars and planets were fixed in the universe and that these particular arrangements occupied a defined space. However, we now understand that everything in the universe is in motion. Planets orbit stars, stars move within their galaxies at different rates, and whole galaxies move quickly through space, the ultimate fate of which we still cannot predict. Today, researchers are challenged to accept uncomfortable insights, and it is understood that hypotheses are not just theories or major insights until they are thoroughly tested or confirmed by definitive observations. The idea of the Big Bang emerged from the confirmation that galaxies are moving away from each other, and this distance is proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe has been expanding for a long time. Additional proof, like cosmic microwave background radiation and the redshift of light from distant galaxies, as well as other galactic patterns, appears to support this theory. Nonetheless, it is important to remember that people who once believed the Earth was flat and that the Sun revolved around us also had similar types of evidence for their doubts until events or technological advancements provided a clearer and more accurate picture. Present, we are seeing a similar situation. Researchers expected the JWST to confirm suspicions about the Big Bang, but instead, they have found the 6 galaxies that appear to be too large for their age. This reminds us that science is always evolving, and experts must remain open to new discoveries and rethink existing theories based on available evidence. Researchers use redshift as a tool to determine specific measurements in the study of the universe. Redshift, otherwise known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to each other. To understand this, imagine watching a vehicle coming toward you. As it draws closer, you hear the engine getting louder. However, once the vehicle passes you or moves away, the sound changes. This is because the sound changes as the vehicle moves. The same is true for light. When a light source, like a distant star, moves toward us, the light we see shifts toward the blue end of the spectrum. On the other hand, when the light source moves away, the light shifts toward redder hues. This phenomenon is known as redshift. Physicists have converted redshift values into speeds and distances for estimating quantities in the study of the universe. Nevertheless, it is crucial to note that small errors in these calculations could have tremendous implications. The measurement methods used in the past are now under review, and the results that researchers will arrive at regarding the latest revelations related to our universe are exciting. It is important to consider whether these results are genuinely based on redshift errors or whether some scientists are simply denying the facts. This is a question that requires serious assessment and careful review of the data and methods used in the investigation. As scientific inquiry progresses, discoveries made by instruments like the James Webb Space Telescope frequently challenge our assumptions about the universe. The ongoing discovery of 6 monstrous galaxies tracing all the way back to the beginning of the universe is one such example. These galaxies, which defy regular speculation about galaxy formation, raise significant questions about the timeline and processes involved with the development of large-scale structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is equipped with cutting-edge technologies that allow it to peer further into space with striking clarity. Its ability to detect light from the farthest reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and gigantic galaxies challenges existing models that predicted such enormous structures should have formed much later in the universe's history. The implications of these revelations extend beyond astrophysics and into the realm of fundamental physics, compelling scientists to reconsider established theories about the early universe. These discoveries also highlight the importance of remaining open to revolutionary ideas and changing our understanding based on experimental evidence. Kaku has emphasized the critical role of scientific proof in shaping our perception of the universe, pointing out that theories must continually evolve to accommodate new information. The debate sparked by these revelations mirrors the dynamic nature of scientific inquiry. On one hand, there are defenders who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic evolution than previously thought. This viewpoint challenges the conventional view that galaxies develop slowly over billions of years through mergers and the gradual evolution of smaller objects. On the other hand, skeptics caution against hastily discarding established models based on limited observational data. They advocate for a more cautious approach, suggesting that anomalies in data interpretation or measurement errors could explain the unexpected discoveries. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a crucial role in these critical investigations. As galaxies move away from Earth, the light they emit shifts toward longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy's light spectrum, astronomers can infer its distance from Earth and its speed relative to our own galaxy. This data is essential for developing models of galactic formation and understanding the expansion of the universe. However, redshift measurements also carry inherent uncertainties that can complicate the interpretation of astronomical findings. As researchers explore the farthest reaches of space with tools like the James Webb Space Telescope, the importance of constantly re-evaluating hypotheses based on new observations cannot be overstated. With each new breakthrough, scientists like Kaku remind us that the universe is full of surprises. As new observations challenge long-held assumptions, it is essential to approach the study of the cosmos with an open mind. The discovery of ancient and massive galaxies not only pushes the boundaries of our knowledge, but also serves as a reminder of the ever-changing nature of scientific discovery. These remarkable findings are just the beginning, and as technology advances and our understanding deepens, further revelations about the universe are likely to emerge, reshaping our view of the cosmos once again. As scientists continue to analyze the discoveries made by the James Webb Space Telescope, JWST, the implications of the findings stretch far beyond just the realm of astronomy. These ancient and enormous galaxies, which seem to contradict previous models of the early universe, are forcing a re-examination of our understanding of galactic formation, cosmic evolution, and the very nature of time and space. One of the most significant aspects of these discoveries is the possibility that the timeline for the development of large-scale cosmic structures may need to be rewritten. Previously, astrophysicists had posited that large galaxies like the Milky Way could not have existed so soon after the Big Bang, as it was believed that smaller, less massive galaxies formed first, later merging to create larger ones. However, the 6 enormous galaxies discovered by the JWST are not only far larger than expected, but also seem to have formed in a very short period, suggesting that galaxy formation may have been more complex and rapid than we initially thought. This challenges the established model of the cosmic dawn, the time period when the first stars and galaxies began to emerge from the dark ages of the early universe. In the past, scientists had assumed that galaxies formed gradually over billions of years, starting from smaller seed galaxies that eventually grew through mergers and star formation. However, the JWST's findings are forcing scientists to reconsider whether such a slow process was accurate. Instead, these discoveries hint at the possibility that massive galaxies could have formed much earlier than expected, in a way that was not previously thought possible. Furthermore, these findings could have profound implications for the study of dark matter and dark energy. The presence of such massive galaxies in the early universe may indicate that our understanding of these mysterious substances, which make up most of the universe's mass-energy content, needs to be reconsidered. Dark matter, which does not emit or interact with light, is thought to play a crucial role in the formation and behavior of galaxies. However, the formation of these massive early galaxies challenges the current theories of how dark matter behaves and how it might have influenced galaxy formation. The discovery of these galaxies could also open new doors for exploring the nature of black holes. Supermassive black holes, which are believed to reside at the centers of most large galaxies, may have formed much earlier than previously thought. Their presence could have been a driving factor in the rapid formation of these galaxies. If these galaxies were able to form so quickly, it is possible that the supermassive black holes at their centers grew simultaneously, providing crucial insights into how black holes and galaxies evolve in tandem. Moreover, the discoveries made by JWST could push the limits of our understanding of the Big Bang itself. The Big Bang theory has been the cornerstone of cosmology for nearly a century, explaining the origin and expansion of the universe. However, These newfound galaxies present evidence that might not align with our current models of how the universe expanded and cooled in its early stages. As a result, scientists may need to update their cosmological models to account for these new findings, potentially revising our understanding of the very birth of the universe. As new data emerges, the field of cosmology is likely to undergo a significant transformation. The discoveries made by the JWST will undoubtedly inspire future research into the origins of the universe, the formation of galaxies, and the nature of dark matter and dark energy. While it is too early to draw definitive conclusions, the fact that these findings challenge long-standing assumptions demonstrates the power of observational technology in advancing our knowledge. As scientists continue to study these extraordinary galaxies, the potential for groundbreaking discoveries in the field of astrophysics is vast, and we may soon find ourselves rewriting some of the fundamental laws of the universe.